This is problem number 2 from the 2021 AP Calc BC exam. It's a parametrically based problem here, and they tell us that a particle is moving in the xy plane. Its position is given by a set of parametric equations. X is a function of t, y is also a function of t. What they tell us is the velocity vector for this situation. So the x component of velocity, pretty crazy formula for it. And not much of a nicer one for the y component of velocity. They do tell us that at time 0, the position of the particle is negative 2 comma 5, and they ask us to do things that, if you've practiced enough of these problems, you've probably done things similar to yourselves. So part A asks us to find the speed of the particle at 1.2. So the speed at a given time is going to simply be the magnitude of the velocity vector. So we basically resolve the x and y components of velocity and figure out what the magnitude of the resulting vector would be, which is as simple as applying a Pythagorean theorem calculation to your velocity vector at time 1.2. So calculators in play. I didn't have to type this into the calculator. What I have right here would receive full credit. I went ahead and tried to make sure this was going to match what you would have seen in the scoring guidelines if you're looking at those. The other part of part A asks us to find the acceleration vector of the particle at time 1.2. We don't need the acceleration vector in general. If we did, we'd have to try to find a way to take the derivative of these velocity components. But as long as we recognize that, all we need is the derivative of the x component of velocity evaluated at 1.2, comma, the derivative of the y component of velocity evaluated at 1.2, we can use the calculator to produce those numerical values. So you see my TI-83 input here, and rounded to 3 digits beyond the decimal, these are the x and y components of acceleration. The nice thing about the calculus work that we're doing right now, there's no need to try to resolve this vector, to try to determine an angle or a magnitude. We can just list this result component-wise. And so that's one nice little advantage we have here at the tail end of our acceleration portion of the problem. Now we're asked to find the total distance traveled over the interval from 0 to 1.2. So the way that you're going to determine total distance traveled is you're going to do the integral of speed. You do that with motion along a line. You also do that with motion along a curve. I guess in this case, this is also the curve length calculation for this set of parametric equations. So I have basically the exact same thing you saw me using in part A to find the speed at 1.2. I have that with t back in place of the 1.2s, and I've tossed it into an integral. I'm trying to accumulate all of the tiny changes in position across this entire curve from 0 to 1.2. Calculator's in play here, so you can evaluate this with the calculator. I didn't screenshot my input here. I did this on my handheld rather than my desktop calculator just because it's a little nicer. Just be careful with your grouping symbols here. You've got a lot of grouping symbols that are necessary to use to get this in successfully. But as long as you are careful, you should end up with the result that you see right here. And then in part C, and this is where I'm assuming the majority of the points for this particular problem are going to be associated. There's quite a bit going on within part C. It asks us to find the coordinates of the point at which the particle is farthest to the left. So I think farthest to the left. Well, if I'm farthest to the left, I know my x coordinate is as small as possible, so x is minimized. If x is minimized, I need to find the critical numbers of my x coordinate, which would mean what values of t make the derivative of x, make x prime of t, which is simply our velocity component for x, what values of t make that 0. So I set my velocity component for x equal to 0. This is already factored, so I get a solution from that first factor set equal to 0. That's pretty nice. And I don't get anything from setting e to the t squared equal to 0. E to the t squared is always going to be positive. So if I think about what's going on with x prime of t, what's going on with my x component of velocity, I get a negative x component of velocity between 0 and 1, and then I get a positive x component of velocity throughout every other value of t. What that tells me is that the x coordinate of the particle decreases from 0 to 1, and then it's going to increase for all values of t above 1. That tells me the particle is farthest to the left at time 1. I need to know the position, right? It says find the coordinates at this time. So we've identified the time. Now I need the coordinates. Well, the x coordinate at time 1 is going to have to be based off of the x coordinate that we know, which is the x coordinate at time 0. So I'm taking the x coordinate at time 0, and then I'm adding on how much the x coordinate changes by from 0 to 1 by integrating the rate of change of the x coordinate, by integrating the x component of velocity. Calculator's in play, fire that into the calculator. You should end up with this number for your x coordinate at time 1. Do a similar calculation for y, so I obviously have a different initial position that I'm basing this off of, 5 for the y coordinate rather than -2. Still need to know the change in the y coordinate this time from 0 to 1. So you see the y component of velocity is what I've integrated here, right? You need to know how much the y coordinate changes by from 0 to 1, integrate the rate of change of the y coordinate, the y component of velocity, from 0 to 1, and you'll get that answer. And you see the end result is here. Now there is a secondary part here that we're going to have to click ahead to a new screen in order to show the conclusion for, but it says explain why there is no point at which the particle is farthest to the right. So, time is going to begin at 0 and then work forward, right? For time that's positive, my x coordinate decreases from 0 to 1. I hit my farthest position to the left at time 1. But then from time 1, the rest of the way to infinity, my x coordinate is just going to increase, 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 increase forever. And so the concluding statement I made here, x coordinate of the particle is going to increase for all times above 1. Therefore, there's never going to be a time when the particle is farthest to the right.